Well, let's talk about a different approach to some of these kinds of problems. We showed a couple of lectures ago that both climb and acceleration came from the same curve, right? That we assumed that if you didn't climb, then your thrust horsepower in excess gave you a certain acceleration, or if we didn't accelerate, it gives us a certain rate of climb. Well, we're going to talk about the other side. We've looked at rate of climb, now we're going to look at acceleration. One of the things that happened was that with the advent of high-performance jet airplanes, the steady-state climb approach didn't work very well. Number one, airplanes like the F-15 and the F-22, you can't achieve a steady climb at sea level. I mean, both of those airplanes will accelerate going straight up. So you had to come up with some other way of doing this. The other thing that showed up even earlier than that was that this method that we did here and we just finished talking about has a problem. If the airplane has fairly high performance, we get into a problem with the change in airspeed versus altitude as you're changing altitude, or the DVDH term. And with this method, we essentially ignore that term. That's one of the reasons that using this approach, we only take it at that, we take a slope at that one altitude, rather than doing all of those points, okay? We're kind of alleviating the problem with DVDH, okay? Because, you know, as you go up in altitude, due to the change in density, the speed changes. Okay, so back in the 60s, that kind of raised its ugly head, and there was a fellow who at that time was at Douglas. You know, that's a company that's gone its way, but Donald Douglas, you know, was one of the kind of starters of the airplane industry, along with Bill Boeing and
DC-3s.
Yeah, you know, that was what, essentially, when he built the DC-3, he always put himself out of business, and then when he got to the DC-9, he did put himself out of business, because he, you know.
Why? Wasn't the DC-3 successful airplane?
Oh, the DC-3 was a very successful airplane. I mean, you know, hey, I went to war on the DC-3, okay? So, you know, DC-3s were around for a long, long time. In fact, the first airplane that we modified for the gunship program had its first IRAN, which means an overhaul, essentially. Had its first overhaul the year I was born. And this was in 65, okay, when we did that airplane down in Miami. So, yeah, DC-3s were around and were used very extensively in World War II. And a little side note, one of the things that we found, we modified 17 airplanes down at what was then Air International on Miami Airport.
Is that Bassett for the same company?
I don't, well, they became Butler Aviation, and I don't know who Butler has since gone to. But anyway, we got 17 airplanes out of the boneyard out of Davis-Monthan, and they flew them to Miami, and so we made gunships out of them. And we got to, you know, we were trying to document this stuff, so one of the things we found is that all the drawings for DC-3s are well, not around. And the other part was that although the airplanes all looked alike, nothing was in the same place. Major frames were not in the same location inside the airplane. I mean, like I say, they look like on the outside, but then even some of them, we couldn't figure out why some airplanes were as much as 6 inches longer than others. Until we got into the logbooks. All of those airplanes that were 6 inches longer had been glider tugs during World War II. Some of the airplanes, we pull the floorboard up and there'd be that much coal dust in the bottom. Again, back to the logbooks, Berlin Airlift airplanes, which had hauled coal into Berlin so that people could stay warm. I mean, that was the kind of, it was a history lesson. Doing those airplanes was a real history lesson. It was just amazing. But anyway, those are some great airplanes, but getting back to Donald Douglas, of course, he made a bunch of airplanes since then, but when he made the DC-9, he had a problem getting engines, and they had a whole bunch of inventory of airplanes without engines, and that forced the company into merging with McDonnell, okay, McDonnell Aircraft in St. Louis, okay, who was building the F-4 and those kinds of airplanes at the time. And of course now Boeing owns the whole thing, okay, so yeah, it's the thing. But anyway, Ed Rutowski worked for Douglas, and he came up with the idea of this energy methods. He's credited with doing that. So we'll talk a little bit about energy methods. Well, essentially, you know, it starts from the fact that the total energy of a system, doesn't matter whether it's airplanes or barn doors or whatever, is that you have, you know, how high is it? That's the potential energy. How fast is it going, so to speak, is the kinetic energy. And so we can write this thing, you know, the total energy is the weight times the height plus weight times velocity squared over 2 times the acceleration due to gravity. And to normalize the equation for weight, why, we come up with a term we call the specific energy, E sub S, and it's just the total energy over the weight of the airplane. And E sub S, when we do that, looks like that. Well, that's beginning to be a kind of a familiar equation, isn't it? But E sub S by itself doesn't tell you the performance. It has its units in feet or meters, if you use, depending on which system you use, and it's sometimes called energy height because it, you know, is in either feet or meters. And you can plot up lines of constant specific energy, and they look something like this. Okay, so this is altitude, this is airspeed or Mach number, and this is a line of a constant specific energy. Notice up here, it's all height, or all potential. And over here, it's all kinetic. It tells us our energy state, but not what our performance is. So, to define the performance, we have to determine how the energy state changes with time. So we take and we differentiate it with respect to time, and now we have dH dt. We sometimes call that rate of climb, right? dH dt plus the acceleration v over g times dv dt, or the acceleration. Well, if you notice, that's the same as the thrust horsepower in excess equation divided by the weight. So if we take that and divide it by the weight, we come up with a new term we call the specific excess power, P sub S. And P sub S, you know, is just that derivative. And that also equals the thrust horsepower in excess, which we talked about before, over the weight. Now, if we plot lines of constant P sub S on our specific energy plot, then we can define the performance capabilities of the airplane. Here's a subsonic airplane. Now, what's confusing about this to most folks, including myself, is that this is, you know, we talked about that rate of climb plot, how we got, you know, if we did different airspeeds, how we got that different rates of climb, and that the anchors were stall speed and power on stall speed and maximum level flight speed, and then we had that curve. These look like them, but they're not. They're kind of turned inside out, you might say, okay? Because when P sub S equals 0, this guy, that's the maximum performance of the airplane. This is as high as it can go. This is as fast as it can go. Okay, and then again, down here though, that's still stall speed, since that's, you know, and this is increasing P sub S, where the other plot we had of rate of climb, you know, as the curve got smaller, that was smaller rate of climb, right? Well, here, you know, this is a greater rate of climb than this. Here is 0 rate of climb. Here is, you know, maximum rate of climb. Yes, sir?
When we talk about velocity and altitude, we're talking about density, altitude, and to airspeed, or we use indicated and pressure altitude?
You can use either one, I think, okay? But generally, this would be a true airspeed plot. Now, this is for a subsonic airplane, and like I say, this outside plot is the performance envelope of the airplane. Now, when we go supersonic, here's what the kind of thing that happens. It grows a cancer. Right? It gets a big cancer out here. This is Mach 1, okay? So, what does that tell you about the airplane? How, if you wanted to get to this maximum energy state out here, how would you get there? What's the fastest way to get there? Well, you would climb along this plot where these lines of constant specific energy are tangent to the P sub S lines. You'd climb along that, get up here, and then you would dive along a constant energy line to go supersonic, and then climb out this way.
Which is the envelope, the last one, right? The PS equals 0. Is the envelope?
Yes, that PS equals 0 is the outside, is the total envelope of the airplane. So if you were flying an interceptor airplane and you wanted to, you know, intercept an incoming bad guy, and you wanted to get up to him in a hurry, you know, you'd go like this, dive, go supersonic, and go out like that. So you can see the drag of what's going on here. This is a transonic drag rise. Now, I suspect they still have it, but back during the days when we were concerned we were going to have to fight the Soviet Union, fighter pilots in the U.S. had plots of this for all of the competitive airplanes. So they knew where to go to have an advantage. They had a plot of that, which they could overlay this data from their own airplane, okay, and tell where it was, what speed and altitude it was best to get to have a performance advantage. So that was one of the ways this stuff was used. And there were, you know, there were little guys around with these funny little small cameras, you know, taking fuzzy pictures of Russian airplanes to, and from, you know, those fuzzy pictures and photogrammetric techniques, they could come up with these kinds of plots. And a few other things, but anyway, that's was one of the uses. Well, we can apply them to climb performance. Once we know excess specific power, P sub S, you can determine climb performance by assuming that the acceleration is zero, okay? So as a flight test method, we can say, okay, well, we just won't climb, we'll stay at an altitude, and we'll accelerate, and we'll measure the acceleration, and then we can calculate the climb. So on very high performance airplanes, high performance fighters, that's the method, as opposed to doing steady climbs. And so that is the one we will do in this freebie flight, okay? And how you do that test, you get to the altitude you want to test and you slow way down, just above stall speed. Record your parameters, your altitude, your temperature, those kinds of things. And of course, you're not going to be at full power at that time. You're kind of sitting there, sort of hanging on the prop, so to speak. And you go to full power and start your stopwatch. And every so many seconds, you read the airspeed. So what you get is a plot that looks something like this, where you have time and airspeed, and you'll get a curve that'll look something like this. I show this point, this area right in here. What happens, this is pretty small. It may be hard to see this sometimes in the data, but you need to get that. Because when you plot this thing up, if you just say, oh, that's just data scatter and plot it like this, what happens is you only get half of the curve, you know, because now from this you're going to develop, you know, you're going to develop this rate of climb curve. Except if you don't get this little plot, see, that's this part of the curve. So if you don't, you know, if you just straight line that there, you only get this half of the curve. So you need to, you know, you don't need to ignore that point. Now, with a high performance jet airplane, this is going to be much more pronounced than it is on a Cherokee 6. And why is that the case?
Good velocities can pick up a lot.
Remember, this is a power curve, right? And how does a jet airplane develop power?
Through airspeed.
Thrust and velocity, right? So what happens, what kind of a curve do you get for a jet airplane for power, what? It looks something like this, right? Where this is power, and this is velocity. It's pretty much a straight line from, you know, say this is 0 airspeed. As you increase in airspeed, you know, because power is equal to thrust times velocity. So if you plot, you know, the power, or let's say we plot a power required curve on here. A jet airplane's best rate of climb speed, which is the maximum difference between these two curves, is going to occur at a much higher airspeed than an airplane like the Cherokee 6. Because its curve looks more like this. So, you know, the maximum difference between these two curves, this one's gonna occur at a higher airspeed than that. So most jets, if you've flown a jet airplane, you'll find that you climb at a much higher airspeed, even though the airplane may be somewhat comparable to a light airplane. For instance, the T-37, which I flew as a fledgling pilot, you climbed at a much faster airspeed than you did, you know, on most GA kinds of airplanes because of this relationship. So what happens here, and before I go away from these curves, what happens is that when you do this level of acceleration, when you do this curve, you are developing this whole curve. Now that may be a way to determine what the best rate climb speed is for even a light airplane. Because what did I tell you we had to do to determine the best rate climb of, say, a Cherokee 6? We got to go up here and fly climbs at all these different airspeeds, you know, to define this curve. That takes a lot of time. That only gives us one altitude where we could go up and do an acceleration. And I'll be real honest with you, it isn't worth going more than 1.5 minutes. Because once this curve flattens out, you don't care. What's, you know, the interesting part of this acceleration curve